So now that we've defined the background and what a concrete and abstract data structure are, we can talk about linked lists specifically. And a linked list is a concrete data structure, and it is a sequence of nodes. So we literally need one node, and that's all we need. We need the head node of a linked list. And like picking up a chain, if you have one link in the chain, you have the entire chain. It's the same concept here. If we have our head node, we can find the first node in our sequence, and then we can just follow the links through and get every single node. We've defined concrete data structure before, just a moment ago. And the key fact here, the reason why I bring it up again, is that I want to bring up that arrays are another type of concrete data structure. And in this module and for the rest of the class, when we talk about a solution using an array, we're also going to want to compare how would it be different if we implemented with a linked list. These are going to be alternatives to each other. And when we get into our analysis towards the end of this module, you'll see that what one is strong at, the other one isn't necessarily strong at. So it's good to have these alternatives, right? It's good to be able to make a design decision. Remember, there's no such thing as a bad design decision if you can justify it. If you understand the strengths and weaknesses of what you've decided and can justify why those weaknesses are acceptable in this case. The only bad design decision is one where someone goes, "Why'd you do it this way?" And you go, "I don't know." That's not a good decision. You can say, well, computationally, they're roughly equivalent. The amount of memory difference is negligible, and I found this approach to be easier. So it should mean that my implementation will be easier, less buggy, more direct, and more extensible. Done. Great answer, right? And this is not just school. This is work, too. And if other people can't understand why you made a decision when you're designing code, they're going to question your decisions on other things too. And frankly, if you can't explain it, then there's the risk that you made something that's insecure, buggy, or possibly just doesn't do what you need. So, okay, we've got arrays and we've got linked lists. A linked list is a data structure consisting of a sequence of nodes. Okay, and all we need is a reference to our head node. So then what is a node? What is a node? A node is a single element in a linked list, and it operates similarly to a single slot in an array. It is the thing that contains the data. It contains the element that's being held. We can call it a data point. We can call it an element. We'll go back and forth on the two things. And it also contains a pointer or a reference to the next node. So when we draw it this way, this is what it is. This is how it's actually implemented in memory. Okay. You will see me sometimes, if I may draw our node like this. Okay, with the element inside of the block as opposed to this where it's referential. Okay, understand that this is a shorthand, but that I always mean this. Okay, and we can't break this down. This isn't a metaphor. Okay? We have an object somewhere out in memory that has a reference to the data we're storing and a reference to the next node, which is another object out in memory that contains its own data element and its next node. And do not get this and this confused. Okay? This big box here, this is our node. Our data is what goes into the bucket, and our node is the bucket. So you will, when you're thinking about things, start comparing nodes and elements. And you're going to be confused. Why can't I compare these two things? Well, it's because you're not comparing what's inside of the nodes.